16, and we are going to talk about how you name acids and bases, and it's kind of crazy. It's a little tweak to it compared to naming ionic compounds, but the reason why it's included right now is because there are ionic compounds. So there's just a couple little weird things to remember. I'm really going to focus mainly on 6 of them that I want you to recognize for the acids. You'll see a lot of other ones, but we'll try and get as much done in the practice together as we can. I'm planning on a quiz on Friday on putting together and naming ionic compounds. It's kind of like what we did with the lab. We're going to do a bunch of practice tomorrow and some more on Thursday, but most of Thursday in this class and 6th period is going to be tied up with watching the live stream from NASA. So you may have heard, I hope you have, that we are landing another rover on on Mars, and it took off 7 months ago, and it is going to arrive at Mars tomorrow, or no, we can do Thursday, 2 days from today. So yeah, we'll talk more about that tomorrow and Thursday, of course. So pretty exciting. It's really a big deal. And so I want to make a big deal of it. And yeah, that's what we're going to do. So here we go. You might recall that on Friday, we did a little sorting with pH of different substances. I gave you this note sheet in your classwork feed, but we didn't even begin to get close to it. So it is still there. I put it in to week 7. I moved it from week 6 into week 7 so that you can find it more easily. Okay. And then also there's another document on it that's going to be what I want you to do for homework. So we'll get to this mistakes in polyatomics tomorrow, but this is the note sheet and this is the homework. Okay. And so I'm going to close that and we'll come back to that. And let's do this. So this is still in chapter 9. It's the last section of chapter 9, but there is one more section that we'll do in a couple of weeks on covalent compounds. We've done the monatomic ions, the polyatomic ions, and ionic compounds, and then this one on acids and bases. Some of you may have been bitten by an ant before, and it kind of stings. There are some that give a really nasty bite, some big red ants, but around here, they're just kind of a little bit of a bite, but it's still irritating. And that's because they excrete formic acid. It has a real distinct odor. So any of you have ant problems in your kitchen have probably smelled that before, or if you get outside and you get ants on your legs and you stomp on them, they make kind of a weird odor. But formic acid is a colloquial, but it's not a correct name for the acid. We'll talk more about that tomorrow. As you found out on Friday, most things that you ingest, or very many things that you ingest, are acidic, which is usually surprising to most people. And most things that you clean with are basic, and that usually does surprise some students. Strong acids and strong bases are really nasty. There's no good or bad, but you know, most people like lemon juice or orange juice, and vinegar is used in a lot of things like salad dressing and preserving cucumbers and such. Yeah, acids are part of our diet, believe it or not. Okay. We're going to learn how to name acids and write their formulas, but first we have to know what an acid is. And acids are simply compounds that contain hydrogen ions or form hydrogen ions when they go into solution. So acids have hydrogens. Notice the positive charge. That means it's the cation at the front. So hydrogen, positive, fluorine, nonmetal, obviously an anion negative, and they can stick together because the hydrogen ion and the fluoride ion are both the same magnitude, right? So hydrogen fluoride would be how you would name this if you're doing normal ionic compounds, but of course, it's chemistry, so we gotta mess with your brain. Okay, so we're gonna go over the rules on how to actually name this. The reason why this picture's here is because this acid actually etches glass. So that's kind of crazy. It can dissolve glass. Not nice. So how do they do these little designs, and why doesn't the whole glass dissolve when you're etching it? Well, there's a process where they coat the glass with wax and then scratch off the pattern that they want and remove the wax from the surface of the glass and then dip it into the hydrofluoric acid and it fuzzies up the glass surface. It's kind of crazy. So some of you may have glasses like that. I remember my grandparents having little juice glasses like that. I don't have any in my house right now, but I've seen it before. And there used to be a business downtown that would do that for trophies and such. But again, they're out of business, so I can't show you that either. One thing that I want to mention is when you look at pH, we talked about pH on Friday, little p, capital H. It's the concentration of hydronium ions. So you remember, we use square brackets for concentration, but you remember ammonium is a polyatomic cation, one of only two technically, but it's only one that makes compounds. This one, hydronium, is formed when water molecules come apart. And that seems like a really weird concept, but they can come apart. So I'm drawing in valence electrons on an oxygen atom. Remember, oxygen has 6, and if you remember from our Lewis dot structures, that's a really bad dot. Our Lewis dot structures, you should have 8, right? Everybody wants 8 for an octet. So the way that oxygen gets to have 8, at least part of the time, is to sidle up to some hydrogens. Okay? So that's our water molecule. Notice it's not linear, it's bent. And the reason why it's bent is because, we'll go into this in great detail later, but water is a polar molecule. It has a positive and a negative end. These lone pairs are much more negative. And so a random hydrogen cation will stick to a water molecule, and that's what forms hydronium. So when you measure pH, you're actually measuring hydronium ion concentration, not hydrogen ion concentration. But lots of books and lots of people just kind of shorten it up and say hydrogen. But in reality, those free hydrogens are going to stick to water molecules in solution. We're not going to get to acids and bases until May, but I thought I would throw that at you just for those of you who are interested. All right, 3 rules. All depend upon the polyatomic ion or the monatomic, shouldn't have said polyatomic, monatomic or polyatomic anion, okay? How we name acids. So the formula is H sub N with an X. The H is the cation, always hydrogen. N is a subscript, like H2O for 2 hydrogens. And again, we're going to balance charges, just like we do with regular ionic compounds. And then X is for the anion, the random unknown anion of your choice. Okay? So following this pattern, we need to know whether it's monatomic anion or polyatomic anion. And then if it's polyatomic, is it ite at the ending or is it 8 at the end? I'm going to switch my pen color again. So rule number 1 is regarding acids. that are what we call binary acids. So again, remember that means 2 elements. One of the elements has to be hydrogen. So there's just one more. Hydrogen's the cation, and there's some anion. So these monatomic ions end in IDE. Okay? So the anion normally will be named ide at the end. For acids, this is normally going to be a halogen. Not always, but almost always. And so when you name the acid, you throw on a prefix of hydro. You change ide to ic. And in between our sandwich here, you use the stem. So part of the name of the anion, or the halogen, for example. Okay. A couple things I want to just mention here also real fast for those of you that recall, we learned that for transition metals that can have more than one charge, like copper, we write Roman numerals. Okay, that's all you have to do for this class. Okay, if it has a +1 charge, it's copper 1. If it has a +2 charge, copper 2. The classical system calls this cuprous, and this one cupric. Okay, so depending on the ending, okay, I've got ahead of myself. 4th time today, and I'm jumping ahead on a slide, but this is still valid. Us and ic, +1, +2. Hang on to that thought. Let's just go to the simple binaries. Sorry, I'm getting too far ahead. All right, so you've seen this, I hope, before. It's capital H, capital C, and a lowercase l. You know, of course, that's hydrogen. You know, of course, that's chlorine. You probably know that there's an acid in your tummy, and that acid is hydrogen chloride, except for we don't call it hydrogen chloride. There's another name. It has a concentration of 1 molar. This big cursive M is for molarity, to talk about concentration. When I buy hydrochloric acid, I buy 12 molar hydrochloric acid. So that's 12 times as strong as your stomach acid. Stomach acid's pretty strong. If you've ever had acid reflux, you know how that doesn't feel good in your esophagus. You probably know somebody or heard of people having ulcers, and that happens when the mucus lining of your stomach is broken, and the acid from your stomach causes an irritation. All right, so again, we don't call this hydrogen chloride, even though it's hydrogen with chlorine, and the chloride ion is what it's composed of. We change that ending, and we add hydro. So we shorten up hydrogen to hydro, change I to ic, put it all together with the word acid, hydrochloric acid. That is one of the 6 acids you do really, really, really need to know for our class. Okay? HCl, hydrochloric acid. All right, here's where I was going with the ic and us stuff, so hang with me. So ternary acids, binary acids just have 2 elements, ternaries have 3, maybe more, but usually that 3rd one is oxygen. So sometimes these are called oxy acids, obviously if they have oxygen. You know that most polyatomics have oxygen. There's some nonmetal with 1 oxygen, 2 oxygens, 3 oxygens, 4 oxygens. This depends, and it doesn't necessarily have these charges, but let's just start there. Are all negative. So like we have to keep in mind that these have different endings. Remember, ite ending is for the fewest oxygens, or at least one less than 8. That's why we learned our Nick the Camel thing. So I wanted to just mention that all the time, this is one of those all the times that I think I can tell you. If there's 2 oxygens in a polyatomic, it's always going to end with ite. Okay? If there's 4 oxygens in a polyatomic, it's always going to end with 8. It's the ones with 3 oxygens that we don't know which way to go. It depends. Okay? But that is another piece in addition to our Nick the Camel sentence that can help you if you can't remember. So I wanted to mention that. Okay, I'm going to get out of here and come back so it's clear. So again, we're dealing with polyatomic ions that end in ite. The way we name the acid with that ion is we take the anion's name, that becomes the front of the acid name, and the ending goes to OUS. So remember, ite is 1 less or lower number of oxygens, just like Cuprous is the lower charge on copper. And then we throw acid on the end. So let's go through an example. SO3 2 minus is sulfite. Okay. Remember, if we do sulfur, that gives us sulfate. Okay. They have the same charge, they have the same starting element, they both have oxygens. How do we distinguish them? Okay. The first thing that you can do is you can look at this acid. Remember, if sulfite is a -2 and hydrogen is a +1, I need 1 sulfite and 2 hydrogens. Okay, so that's the N number of hydrogens. So we do make their formula the same way we make any ionic compound based on their charge. This weird looking picture is a picture of a statue that's dissolving away somewhere in Europe. Unfortunately, sulfate with hydrogen and sulfite with hydrogen are part of acid rain, particularly from burning coal. Coal has a lot of sulfur in it, and that makes the rain more acidic than it should be. And so these old statues are dissolving literally away. And I wanted to show you what happens after this infant period. The acid bubbles away the rock. Now you won't see them bubbling on a statue probably, or but lots of things are oh, you guys, there you are being ruined, including the sphinxes and the pyramids. So I want to show you this real quick. Last week I showed you some crystals, I showed you quartz, I showed you some pyrite. I said I didn't know what the pyrite was embedded in, but I needed some acid to find out. So sometimes quartz and marble look really similar. You've seen lots of quartz around here that's kind of white and milky looking. Marble is as well, very often. So the trick that geologists use is putting some acid onto the rock. So they carry a little bottle of hydrochloric acid. And if you put the acid on here, it doesn't look like it's doing anything. It just looks like water. Okay. On the other hand, if I put some acid on the backside of this pyrite sample, it's embedded into, I don't know if you can see that very well. You see the like steam coming off. That is fizzing and bubbling and hissing, and that is dissolving the rock away. Oh, I'm sorry, Julian. So it's dissolving the rock away. Last when I did the second period, it kind of made some big bubbles. But that is a way to test what the background rock is. And so I know this is a calcium carbonate containing rock, and I'm making carbon dioxide gas with my hydrochloric acid. So we'll be doing that more later. So anyway, I just wanted to show you guys that. All right, let's get back to the presentation. Sorry, little side. So again, these statues everywhere are dissolving away. It's really sad. So hopefully somebody's going to figure out a way to coat them to keep them from disappearing completely. All right, next, what do we do with acids, or excuse me, with polyatomics that end in 8? Again, that's got the one more oxygen. And so again, it's a ternary acid. It has hydrogen because it's an acid, and the anion ends in 8. This time we would still base it on the anion's name, the little front part, and then the ending becomes ic. So it's 8 for the poly, becomes ic for the acid. Then of course you write the word acid too. This, hopefully you recognize or starting to recognize some of these. N for nitrogen, 1, 2, 3 oxygens, -1 charge. This is nitrate. It has a -1 charge. Hydrogen has a +1 charge. They're going to go together 1 to 1 to make hydrogen nitrate, except we don't call it that. This is a really dangerous acid, and it's really nasty too. It dissolves a lot of things, including pennies. So later in the year when we do chemical reactions, I'll be putting a penny into some nitric acid and showing you what happens. You can tell it's copper here because of the green, and then this nasty gas that forms. I have to do that under the fume hood. At any rate, nitric, just told you the name. So it's nitrate. You change the 8 to ic and put acid on it. Most of the acids that you're going to have to know are anions are 8s. Okay, so most of them are going to end with ic. All right, so to sum it up, chlorine becomes chloride. The acid name gets hydroic. Okay, prefix and suffix. And so hydrochloric acid, super important that you know that one. Ite, with a T, sulfite. The name comes from not the oxygen part, and then we change the ending to us. The ite becomes us, sulfurous acid. This one's weird because we add in the second syllable of the element's name. Most of them we don't. I don't know why, I'm sorry. And then nitrogen is the nitrate ion. Again, nit and ic. So this becomes nitric acid. Questions right now? Okay, so formulas are just in reverse. So remember, formulas have symbols. So when I look at this name, hydrobromic acid, the hydro tells me right away it's a binary acid. We don't use hydro on any of the polyatomic ones. Okay, and brome, so we know there's hydrogen, and brome is for bromine, and that's a halogen, right? Fluorine is fluoride, chlorine is chloride, bromine is bromide, iodine is iodine. So it's -1 with a +1 hydrogen. I've got the formula right now. HBr way down here. So that's pretty simple. It's a little bit harder when you're trying to go from, I don't know, phosphoric acid to what it is. But these are the 6 that you really need to know. And I will include at least one of these on Friday's quiz. So hydrochloric acid, HCl. Sulfuric acid comes from the sulfate ion. Nitric acid, as we just saw, comes from the nitrate ion. This one's a little weird. Okay, so this is the hydrogen, but notice it's on the back side. It's really confusing. It has to do with the shape of this polyatomic. This is this acetate ion. And on your papers, it's C2H3O2. Has a -1 charge. Hydrogen's still a +1. They typically flip it because this end is the reactive end, and we'll talk more about that. Again, it's acetate. Phosphoric acid, how do I figure out the charge? I go, oh, 3 hydrogens, +1, +1, +1. Right, phosphate is PO4 3-. And then carbonate is carbonic acid. So I know it's CO3. What's its charge? Oh, 2 hydrogens, so it must be a -2. The first 3 are very strong acids. They completely dissociate in water. They're pretty dangerous. Sulfuric acid, of course, is in car batteries. It's like in your stomach for hydrochloric. And then these are typically what we would classify as weak acids. They don't completely dissociate, although full-strength acetic acid is pretty dangerous. Phosphoric acid and carbonic acid are in beverages, bubbly beverages, and then, of course, acetic acid is common name. All right, bases are amazingly simple, okay? How do we know something's a base? We know that if it has hydroxide. For now, that's our definition of a base. There's more than one way to explain it, but that'll work for us. Hydroxide ions are anions. It's a polyatomic, right? Real quick, this is an important type of reaction. Hydrogen ions from an acid, hydroxide ions from a base come together to make water. Okay? That's called neutralization. So if you have equal numbers of hydrogens and hydroxide, you got water. Okay? You will always have some in a neutralization reaction, and you may not have exactly equal, but we'll talk about titration in May. So hydrogen, hydroxide makes water. Actually, really clever way to think about water as hydrogen hydroxide. It really makes it easier to do these ionic reactions. Happy person cleaning their oven. That is not me. Okay, I don't know who would be happy about doing that, but anyway, bases are used for cleaning. This is, I just have to emphasize this is mislabeled. It's really ammonium solution, not ammonia. Ammonia is a gas, NH3. When you mix it with water, it literally rips hydrogens off of water. Okay? So our water molecule becomes hydrogen hydroxide. I've done this for you previously, but I'm just going to draw it right now really quick. When I talked about ammonium, the hydrogen is able to stick to sticky lone pair on the nitrogen, okay? And we end up with the ammonium ion. So that's what's really happening. So we've got ammonium, this hydrogen right here, and hydroxide in these bottles. And it's the hydroxide that makes it a good cleaner, that cuts through grease, which is why they put it in the window cleaner to get rid of those streaks. Okay, it's a very strong base. It's nasty stuff. So is sodium hydroxide. I buy sodium hydroxide, and it comes in these little pellets. It absorbs water from the atmosphere. I'll show you that later. If you make soap, you might buy it in these flakes. You can also purchase it, I think most of the time in the cans, it's kind of flaky. Also, its common name is lye. It's used in oven cleaner and drain cleaner. It literally dissolves away everything. It's nasty, nasty stuff. and it's a very strong chemical irritant to your hand. You don't want to get it on your skin, that's for sure. It bothers me way more personally in my skin than any of my acids. So it's crazy stuff. All right, bases are named the same way you name any other ionic compound. You name the cation, you name the anion, you're done. Super simple. So this is Al, not Ai. Remember, this is a lowercase l. So we've got aluminum. You know, aluminum's a +3. It's in group 13 or 3A. Hydroxide, -1, -1, -1, right? We wrap up our polyatomics pretty. In parentheses, put the subscript on the outside because we need 3 of the whole thing. How do we name it? Aluminum, hydroxide. Boom. It's that easy. Okay, so we're just using our crisscross, right? 1 aluminum, 3 hydroxides. Make sure you wrap it up in parentheses. Okay, and the last little picture from your book is a picture of a paper mill, and they say that sodium hydroxide is used in making paper, and it's to help, I guess, to help break down the paper into pulp. Okay, any questions on the presentation? All right, I got 7 minutes. Let's go down on the practice. So I gave you the rules up in the top box. I just want to point out here for the ternary acids, remember most of the most of the polyatomics are going to end in ate or ite. There's those darn chlorines that can have prefixes as well. So that's why that's on here. We just keep the prefixes and we change ate to ick and ite to us. If it's just 2 elements, hydrogen and something else, hydro goes on the front, ick goes on the back. So again, nitric acid, hydrogen's on the front. The ick ending tells me it's nitrate. So I don't know if you want to have your polyatomic ion list or something else, your flashcards that you made. Remember, command comma gives you a subscript. Nitrate is a -1, hydrogen's a +1, all done. Chloric acid is going to be the chlorate ion. So it's C, big C, little l, big O, sub 3. It has a -1 charge, 1 hydrogen on the front. For our purposes, the book has it written the backwards way. I'm fine with you doing hydrogen C2. Remember, we have to undo it. H3O2. The acetate ion is a -1. The hydrogen ion is a +1. This is acetic acid or vinegar. Vinegar is 5% acetic acid. Vinegar is mostly water. So, and we'll talk more about why they do it the other way another time. Hydro. As soon as you see hydro at the front of a name, it's a binary. Okay? So hydro, front of the name, it's a binary. It's fine. There's several others, okay? So again, hydro for hydrogen, brom for bromine, halogen, +1, -1, you're done. I'll do one more, sulfurous acid, H2, SO3. Sulfurous is sulfite, SO3 with a 2- charge is sulfite. All of these have their components down here, so hopefully you can find them. So let's try this one. Chlorine with 1 oxygen. We're doing it in reverse now. That's the hypochlorite ion. So this is hypochlorite, ends with us. Hypochlorous. I separated them just to show you. Okay, you put the hypo, then chlorous instead of chlorite. This is phosphate, so this is going to be phosphoric acid. And then, of course, binary hydrochloric acid, hydrochloric acid. SO4 is sulfate, so this is sulfuric acid. In reality, the ick is attached. I'm just doing it to be goofy, okay? And this is nitrite, so this is nitrous. Sorry, there we go. Acid. Questions on the acids? Just getting used to the little rules. Right, and then the last 6 are really simple. They're just naming the bases. And again, the base, we just name the metal at the front and hydroxide. So K is for potassium. And OH, of course, is hydroxide. Down here, the Roman numeral 2 tells you which copper, so you know how many hydroxides. And then you have to figure out the charge on the metals that they don't tell you because they always have the same charge. All right, that was a lot of information. I hope